Okay. So good evening, everyone. I hope you are doing good at your home and you are good health-wise also. So today we are here with our lecture 3 on KTG and thermodynamics. So in the previous two lectures, we majorly focusing on thermodynamics, not on KTG. But in the upcoming lectures, we will also discuss KTG. Okay. Now, so in the previous session, what we have did or what we have learned about in all the previous session, the two session I'm counting. So in that two session, we have learned about what is thermodynamics, yeah, what is a process, what is path, what is work done, heat and internal energy of a system, and how to decide a system, what types of system we have, what is surrounding, what is boundary, types of boundary, what is temperature. So all of the things we have discussed in our previous sessions. Now, in today's session, we are going to learn about the first law of thermodynamics. Although we have discussed the zeroth law of thermodynamics also and the concept of temperature. So today we are going to learn first law of thermodynamics and thermodynamics process. Okay. Now, before we go deep down in the continuation, we will like to revise the things that we have did in previous class. Okay. So let's just get started. So we have studied about the thermal equilibrium in the previous session. And what is thermal equilibrium? So whenever there is a temperature difference between two systems and we make or combine them, okay, and allow the heat to be transferred from one system to another system, after some time they acquired, or you will see that there is no heat transfer taking place after some time. That condition or that situation we can say is the thermal equilibrium. Okay. So in thermal equilibrium we can say that the temperature of both the system will become same. Okay. So that is the thermal equilibrium. Then we have studied about the zeroth law of thermodynamics. So we have seen that if two systems separately in thermal equilibrium with the another system, so we can say that these two systems also in the thermal equilibrium, or you can say that these three system is in thermal equilibrium with each other. So this is the law of zeroth law of thermodynamics, which basically conveys us to the concept of temperature, because that one thing which is constant after achieving the thermal equilibrium, they are attaining some common value, which is temperature. Okay, so that physical quantity is termed as temperature. Now, thermodynamics, we have already discussed. What is this? It is the study of heat and temperature and interconversion of heat and the other form of energy. So system, a region of space, or I have explained you in terms of focus. So the focus of study is termed as system, where we have put our focus, where we want to analyze that particular region or space. That particular space or region is termed as system. Other than that, all the things will be surrounding. And if you combine system and surrounding, you will have a universe. Now, system was also a thing which specify or characterize, okay, something, and that is termed as the property. So property of any system is tells us about the pressure, temperature and other parameters or other characteristic of the system. Okay. Change of state from one equilibrium to another is known as process. The path that we have followed, or the way that we have followed to change the state from 1 to 2, is termed as path, which is the connection between state 1 and 2. And the way that we have chosen to acquire that state is termed as process. Collection of process, initial and final are same term, is termed as cycle. For cycle, The initial process is same as final process. Okay. So I would like to differentiate between reversible process and cycle. So for reversible process, na, it is not compulsory the process should be same. You can see here, this path is different, this path is different, this process is different, this process is different, but it is completing its value from initial to final. This is initial, and let's say this is final itself, because it is achieving this. So you can say it is a cyclic process, but not, it is not a cyclic process, it is reversible process. But for a cyclic process, this could be the graph. You are following this path by going down and following this path by going up. Same process. That is termed as cycle. Okay. Now, today we are going to learn about first law of thermodynamics, specific heat capacities and indicator diagram, and also how to deduce work expression with the help of this indicator diagram. Hello Virendra, how are you? Now, then we are going to learn about thermodynamics process. Now, firstly, what is first law of thermodynamics? This law is based on good. This law is based on the energy conservation law. Okay? This law is based on energy conservation law. देखो, in every field, we have just completed the fluid mechanics. So in fluid mechanics, you have two law. First, representing the law of conservation of mass. Second, representing the law of conservation of energy, which is law of conservation of energy is represented by Bernoulli theorem, and conservation of mass is represented by equation of continuity. In later on in 12th class, you will learn in current electricity. There are two law, Kirchhoff's law. So Kirchhoff's two laws are based on same thing, conservation of charge, which is equivalent of mass in current electricity, and conservation of energy, which is same as this. Okay. So in both the fields, these two law is universal. Okay. So first law of thermodynamics is the law of conservation of energy. It very simply it says that if there is a system, you have a system, okay, you put some heat into it, you are transferring heat into it, let's say amount of heat transferred to be Q. So if heat is given to the system, it is considered positive. I have already told you about the sign convention. If heat is given, then it is positive. If heat is taken out, it is negative. Now, if heat is given to the system, then system would do some work, because now it is simple like this cylinder piston arrangement. This is the gas. So we are heating this gas up. So because of heating, this gas want to expand. Okay. Got it? If this gas is want to expand by this law, P is equals to KT. P is directly proportional to temperature, Charles law. So if increasing the temperature, the pressure of gas will increase, which means this gas want to expand. So it will apply the force on piston, which means the gas is doing work, or you can say the system is doing work. That should be considered negative. Okay. And also, if you are increasing the heat, which means you are increasing the kinetic energy of the molecules, they will strike with more pace to each other. And kinetic energy and potential energy is nothing but the total internal energy of the system. So by providing heat, there are two major changes in the system. First, the system would or may do some work, and the change in internal energy. Got it? So we can say that this net heat transfer is equals to change in heat transfer is equals to change in internal energy plus doing some work, plus work done. Now, based on the situation, if you are giving heat, it is positive. The work is done by system, that is positive. Work is on the system, that would be negative. Okay. If you press the piston down, you are doing work on the system, which is considered to be negative. Okay. If you are pushing the system up, which means gas is pushing the system up, this piston. So you can say that now gas is doing work and our system is gas. Okay. So work is done by system is taken positive. Work is on the system, then it is taken negative. Heat is provided to the system, positive, and heat is taking from the system or rejecting from the system is taken as negative. Now, so this is the first law I have explained you. So it is based on law of conservation of energy. So the energy can be transformed from one form to another form, but neither created nor be destroyed. This you can say, yeah. So the change in internal energy delta U of a closed system is equals to the amount of heat supplied to the system minus the amount of work done by the system on its surrounding. In simple word, we have provided some heat to the system. It will give us some work and the change in its internal energy. So you can say that delta U is equals to delta Q minus W, or this will be modified as delta Q is equals to delta U plus W. Got it? So no worry about that. Now this is your first law. For reversible process, the work done that we have seen is P into delta V, which came from, if this is the piston you have, okay, and let's say this is the gas inside it. Initially it is at length L. Now the gas has expanded, so system the piston will move up, and let's say the piston has moved from initial position to a position here, and the movement is delta x. Now if you calculate the work done on the piston, it would be force applied by the gas multiplied by the displacement F into delta x. Now the gas is applying force on each and every section of it. So this could be considered, you can consider it to be a pressure. The force is nothing but pressure into area. So work done will be force pressure into area into delta x. Now this A delta x is nothing but the volume that gas has up to the gas has extend. This is the volume because area is a base area and this is delta x. So this you can consider the change in volume. So work done we here will be, now this F will not come, P into delta V. Got it? So from here, this expression has come. Now, so for reversible process, the work done is given by P into delta V. And I have discussed with you that how this come. So work done is P into delta V. So from first law of thermodynamics, we can say that the delta Q, oh sorry, delta Q is equals to delta U plus P into delta V. And all the quantity you have to put with sign. So I am writing it here, careful with sign. Okay. Delta Q is the heat transfer. W is the work done on by or on the system, according to which we will take the sign. And delta is the change in kinetic energy. Sorry, internal energy of the system. Now, limitation क्या है? This law is conveys us that okay, the heat is transferred to the system, but what is the rate of that heat transfer? In which direction that heat flows? It is not conveyed by this law. So this is the limitation of it. So it does not tell us about the direction of flow of energy, in which direction the energy will flow. Okay. and it does not tells us about anything whether the process is spontaneous or not, which is rate of process, how fast the process has taken place. It is not conveyed by this law. Okay, so these two are very important limitation you must keep in your mind. Now, look at the question. A gas is compressed in a cylinder by a movable piston to the volume half of its original volume. Okay, so let's say the initial volume is V. So final volume will become V by 2. Okay, now 300 kilojoule of heat leaves the gas and internal energy remain the same. Now find out the amount of work transfer. This much amount of heat, the delta Q here is 300 kilojoule. It is leaving the gas and internal energy remain the same. Means the change in internal energy is zero, you can say. Okay. Because if energy is same, that final minus initial will be same. And it is leaving the system. So if heat leaves the system, it would be considered negative. Okay. So find out the amount of work transfer. So we can say that delta Q is equals to delta U plus W. Okay. So from here, if this is not changing, delta Q, you can say it is 300 kilojoule. So work done will be minus 300 kilojoule, which means the work is done on the system. Got it? Now, this negative sign shows that the work is done on the system. Got it? Second question. Try it by yourself. Try to solve this question. Giving you 2 minutes. A closed system undergoes a process 1 to 2 for which heat transfer and work transfer are plus 20 kilojoule and plus 50 kilojoules, which means heat is transferred to the system and work is done by the system, respectively. If the system is returned to state 1 by another process 2 to 1, in which heat rejection is 100 return process 1 to 2, and then again we have gone 2 to 1. So in this process, what is given to you? The heat transfer plus 20 kilojoule and the work done is also 50 kilojoule. It is given to you. Now, this is for the process 1 to 2. Now in 2 to 1, heat rejection is 100 kilojoule, which is minus 100 kilojoule. Okay. So what is the value of work transfer in return the process? That is to be asked. Okay. So what we are going to do, you know that I have already told you that internal energy is a state function. And state function depends on that what is the final state of the system and what was the initial state of the system. So in this process, if you will see, we are going to 1 to 2, okay, and then again we are moving back to 2 to 1. So in this, final and initial state are same. So we can say that there is no change. The work, the internal energy will not change. Got it? So this is state 1, this is state 2. So the path that we have taken is here A, and this is before returning it. Now, Q for 1 to 2 is plus 20, work from 1 to 2 is plus 50. Q for 2 to 1 is minus 10 kg, sorry, minus 100. And work for 2 to 1 is being asked. We know that for thermodynamic cycle, in initial potential energy, initial internal energy is equals to the final internal energy. So if I apply this equation, the first law of thermodynamics, so it will be Q delta Q you will write as Q1 to 2 plus Q2 to 1. Work done will be this. Now, putting the values with sign. So 1 to 2, it is rejecting the heat, which is plus 20 kg kilojoule. And in returning, this heat rejection is 100 kilojoule, which is minus, okay, it is 10. It is 10 only. So this will be 20 minus 10 is equals to work done in 1 to 2 is 50 plus work done in 2 to 1 we are interested. So it is minus 40 kilojoule, which means from 1 to 2 the system is doing work, and from 2 to 1 the work is done on the system. Got it? So any doubt anybody in this question? Is this clear to all? If it is clear to all, give me a thumbs up, na? Okay. Okay. Got it. Thank you. Now, specific heat capacities and indicator diagram. Okay. Now, what is heat capacity? First of all, we will study about it. Now, heat capacity is defined as the amount of heat that we required to raise the temperature of any substance or system by 1 degree Celsius. We have provided the heat to the system, and the temperature of the system will risen up. So to rise the temperature by 1 degree Celsius, raise the temperature, which means increasing the temperature by 1 degree Celsius, the amount of heat that we required to give the system is termed as the heat capacity, which is given by S. Look, I will told you what is the concept of that heat capacity. Heat capacity is the heat resistance. It behaves like a resistance or friction, you can say. For any system, let's say you are providing heat. What is the process in which we can see that heat is changing? We will only notify the change in heat because of the change in temperature. Sensible heat. So heat is that factor which can change the temperature. Okay. Or you can say that vice versa, change in temperature cause the heat transfer. Now, this heat capacity is the friction, heat friction provided by the system, which means how much amount of heat it is absorbing to just show the change in 1 degree Celsius. Okay. Which means that system is opposing the change in temperature of it, and that oppose we measure in terms of the heat given to it, that how much heat we should have provided that system to change the temperature by 1 degree Celsius. So it is same as the friction, that how much force we should apply to slide this block. Okay. So that is the concept. So this heat capacity, you purely remember that it is the friction, heat friction provided by the system or any substance. Suppose water required 100 joule of energy to show the change of 1 degree Celsius. Okay. Which means that water is resisting the change up to 100 joule of heat provided. If you provide the heat only 50 joule, should the change will be there 1 degree Celsius? No. Okay. So that is, this means indirectly that water is resisting the heat. Okay. to change its temperature. Now, so heat capacity is the defined as the amount of heat that we required to raise the temperature of any system by 1 degree Celsius. It is given by S. So let's say initial temperature is T1. This is our system. We have provided the heat and the final temperature will become T2. So if Q is that amount that we transferred to the system to change the temperature from T1 to T2, then the heat capacity of the system we can write as S is equals to Q upon T2 minus T1. Or you can say that this delta Q is equals to S into delta, because in the later on chapter you will study that heat provided is somehow linearly proportional to change in temperature. And to remove this proportionality sign, we put a constant which is nothing but the specific heat capacity. Okay, sorry, heat capacity. So this S is the heat capacity here, which is the amount of heat that we require to change the temperature by 1 degree Celsius. Okay, इसकी unit kilojoule per Kelvin. Now, what is specific heat capacity? It is represented by smallest or C. Okay. By C, you can also represent the specific heat capacity. Most of the time, you will see it C. So it is defined as amount of heat required to raise the temperature of 1 gram. Now the mass is also included. Mass is also specified. That is why it is a specific heat capacity to raise the temperature of a specific amount of mass, which is 1 gram. So to raise the temperature of 1 gram of substance through 1 degree Celsius. Okay. So it is small s is equals to capital S by M, because it is the heat capacity to raise the temperature by 1 degree Celsius. Per unit mass, if you will calculate, it will gives you the specific heat capacity. So you can say it that Q is equals to M small s delta T. This formula you can keep in your mind. Okay. So unit of it will be kilojoule per kilogram Kelvin. So we also measure the heat in terms of calorie. You must have heard about it. It is a very common unit of heat that we will use in daily life, calorie. So 1 calorie is defined as to be the amount of heat required to raise the temperature of 1 gram of water from 14.55 degrees Celsius to 15.5 degrees Celsius. Okay, it is also the specific heat, you can say. 1 gram of water has been taken and we are rising the temperature by 1 degree Celsius. So it is nothing but the specific heat. But we are doing specifically for water. So it will be specific heat of water, specific heat capacity of water. Now, you know that 1 calorie is equals to 4.186 joule. Na? And 1 kilocalorie will become 1 kcal, 4186 joule. Okay. Now, to keep the value in mind, specific heat of water is 4.186 kilojoule per kilogram Kelvin or 4816 joule per kilogram Kelvin. Now, molar heat capacity. Here we have used C to represent the molar heat capacity. So molar heat capacity is nothing, only the change in terms of the amount of mass. Here, in that case, In the previous case, we are measuring the mass in terms of gram and kilogram. Here, we will measure the mass in terms of mole. So to raise the temperature of 1 mole by 1 degree Celsius, it is termed as the molar heat capacity. So this will be given by one of the formula you can notice here, that Q is equals to mu C delta T, where mu is the number of mole. Okay. C is the molar heat capacity. So C will depends on, first of all, the nature of substance, although the heat capacity will also depend on that. What type of substance you are taking, what is the temperature of substance, okay, and the condition under which the heat is supplied. Condition means the process that we through which we are supplying the heat to the system. Okay. Now types of molar heat capacity. So we have two types of molar heat capacity, or molar specific heat you can say. So molar heat capacity at constant pressure, Cp, and molar heat capacity at constant volume, which is Cv. Now, so for constant pressure के लिए देखो, in the previous case it is defined as that C will depends on condition under which the heat is supplied. So based on that we have two conditions. First is the constant pressure, second is the constant volume. So if the heat is supplied at constant pressure to the 1 mole of a substance, to raise the temperature 1 degree Celsius, that heat capacity is termed as molar heat capacity of at constant pressure. And if we are supplying heat to the system at constant volume, then you can say the change in temperature by 1 degree Celsius of 1 mole of substance is termed as molar heat specific heat or heat capacity at constant volume. ठीक है? So in this, the pressure will be constant. So the change in pressure is 0. Here the change in volume is 0. Okay. Now comparison if you will do in Cp and Cv for constant volume process, the delta V should be 0. So according to first law of thermodynamics, delta Q is equals to delta U plus W, and which is P into delta V. So this should be 0. The work done, there will be no work done. So total heat is given by the change in energy, internal energy. And we know that this heat is provided at constant volume. So it will be, we can write it as delta Q is equals to mu Cv delta T. Okay. So from that you can see at constant volume, the total heat that we provide is converted into, or we use it to change the internal energy of the system. So you can say it also that at constant volume, the internal energy of the system is given by mcv delta T. Okay. So for constant pressure process, given heat is equals to change in internal energy plus work done by the gas. Now, we know that this change in internal energy is given by mcv, or you can say it mu cv delta T. Okay. So for same change in internal energy, larger amount of heat required in a constant pressure process as compared to the constant volume process. क्यों? क्योंकि for constant volume process, if you will see, the heat is directly going. If you are providing 100 kilojoule of heat, it is directly going to 100 kilojoule of heat is directly going to change in internal energy. But for constant volume process, if you will see here, the 100 kilojoule of heat, some part is going to change the internal energy and some part is going to change the work done. Okay. So to So more work or the more heat, larger amount of heat is required to change in same change in internal energy for constant pressure process. Okay. So for constant pressure process, we need to supply more heat for the same change in internal energy as we have observed in constant volume process. Got it? So do not mix it up. कांस्टेंट वॉल्यूम के लिए जितना हीट हमें चाहिए इंटरनल एनर्जी को चेंज करने के लिए, उससे ज्यादा हीट हमें देनी पड़ेगी कांस्टेंट प्रेशर प्रोसेस में उतने ही चेंज के लिए. ओके, सो आई होप यू गॉट इट. नाउ if you have any kind of doubt you can ask. So we can say that the Cp is greater than to Cv because heat provided in constant pressure will be given by mu Cv delta T, sorry, Cp delta T, and heat provided in volume process is mu Cv delta T. So we know that heat is required more in constant pressure process than constant volume process. So heat given here is larger. So we can say that Cp is larger than C. Okay. Now, can a specific heat of a gas be infinite? Is there any possibility that the specific heat will become infinite? Yes, there it is. क्यों? क्योंकि when I have taught you about the types of heat. So in types of heat, we have discussed the sensible heat and latent heat. Sensible heat is the heat which shows us the change in temperature, but latent heat does not show any change in temperature. So this is delta Q. Let's say mu C delta T. So if the change in temperature is 0, what is the value of C? This is delta Q by mu into 0. So C delta Q upon 0, and something which is divided by 0 will become infinite. In that case, you can say that heat capacity is infinite. Okay, because in that scenario, latent heat is changing the phase, not the temperature. What is indicator diagram? Indicator diagram is nothing. If you plot the curve between pressure and volume, so the final curve you will have, that curve is termed as the indicator diagram. Okay, which shows us the relative change of pressure with the relative change in volume. So this is pressure and volume axis. This is state 1, state 2. This entire curve you can say as the indicator diagram. Now, what is the benefit of this indicator diagram? We know that the work done is given by pressure into change in volume. Actually, it is integration of PdV. Okay. So if pressure is not constant, you can say this is for pressure is equals to constant, and it is VdP when pressure is not constant. Okay. So for this, we are dealing with this. You can say that work done here is P into delta V. Okay. Now, P into delta V, it's somehow, if you see the plot of this graph and you drop this curve, and if you calculate the area under this curve, which is given by this triangle plus this rectangle. Now, all the dimensions you will see here is change in pressure and change in volume. So if you calculate the area of this indicator diagram, this, you have to specify the change here. This is the length of this rectangle, and this length is change in pressure, and this is the change in volume. Okay. So for work done, we know that delta P into delta V, and which is nothing but the area under this curve, which is give you the work done. So area under the PV curve or indicator diagram will provide you to the work done. Okay? So this is the use of it. So by directly having a PV diagram or indicator diagram, you can calculate the work done in that particular process. Okay. And it is also used to assess the performance of each unit of the engine. Okay, because if the area is high, the work done will be more. And if we are getting the work done from the system and our system is engine, so we are getting the more work done. We can relate this work done by heat provided by us. So we can see that by providing how much heat, how much work we have got. So the efficiency of that engine can be measured from this. Okay. So work done, I have already told you. If this is the process, the area under this curve is nothing but the indicator diagram. So it is area covered by that curve will provide you the work done by that system. 1, 2, 3, 4, 1. 1, 2, 3, 4, 1. This area. Okay. Now calculate this. This is the PV indicator diagram is given to you. Initial pressure, you can say it, let's say the process start from here. This is a cyclic process, you can see. The change in pressure is 300 kilopascal, sorry, 200. And change in volume is also 200 cc means centimeter cube. Cc here is centimeter cube. So we can say that the change in internal energy is 0. So all the work done is equals to the heat provided to the system. Okay. And we have to calculate the heat absorbed by the system. So we can say that work done is nothing but the area under this curve. And area under this curve is the area of circle, which is pi r square. Now radius of this curve is here. Let's say this is 200 and this is also 200. So half of it will give the radius, which is 100 cc or centimeter cube. So we have convert this and calculate the work done. Okay. Here the point here to note is that we have acquired a change in pressure delta P with delta V. Okay. Now thermodynamic processes. So based on the data that we have seen, to achieving a state, we need to do a process. We need to follow a path, and to follow that path, we need a process. So in thermodynamics, there are several types of process we will learn. All the process will follow the procedure given by this process, which is quasi-static process. Quasi-static process is very, very, very slow process. It is very multiply by 1000, 10,000 times slow process. Slow process. Okay. And why we are doing that? Because if the process is infinitesimally slow, then we can say that by changing the state, it is acquiring a thermal equilibrium. And we can only state the properties in the thermal equilibrium, not in the changing, not when they are changing. So each and every point of this process is a thermal equilibrium in itself. Almost at rest, which is very, very slow. Okay. So that the system remain in internal equilibrium. This is the stopper. Here the process will stop, and this is the load we have put on. Okay. Now we are constantly removing these loads, the system will move up. Okay, you can see here, you can see, and finally the process is done. Got it? In this we have used more weight. You will see this is a heavy weight, but it is same thing, like we have 1 kg of sand and you are putting one particle of sand. You are taking out one particle of sand in second. So that slow this process would come. Okay. So if you connect these all the points, these are the equilibrium state. So you will have a process. This path is the locus of all the thermal equilibrium state. Okay. Now, the thermodynamics process is defined as the change of state from one equilibrium state to another equilibrium state. So we have isobaric process, isochoric process, isothermal process, and adiabatic process. In isobaric process, pressure is constant. In isochoric process, volume is constant. In isothermal process, the temperature is constant. And in adiabatic process, the heat transfer is constant, which means no heat is given by the system or no heat is given to the system. And that is the purpose of this adiabatic wall. In thermal equilibrium, we have seen heat transfer is zero. Now, isobaric process, we will cover it rapidly. Pressure stay constant. So if pressure is constant, change in pressure will become zero. Volume is directly proportional to temperature here. And also the work done in this process will be zero because there is change in pressure. Not the work done is not zero. Work done is given by P into delta V. So boiling of water on the stove. PV curve कैसा बनेगा? So 1 to 2, because the pressure is constant, so it will be a straight line. है ना? So at all the point of this process, the pressure is constant to this value. Volume is increasing, no worry, but the pressure is constant. Now work done during the isobaric process is given by the area under this curve. Okay? And it is P into V2 minus CV1. Heat transfer, you can also stay with this equation of first law of thermodynamics. Now isochoric process. So isochoric process, that process in which volume of the closed system remain constant. So that process is termed as the isochoric process. Okay. The system should to be closed. Now volume is constant, then we can say pressure is directly proportional to temperature. Now, and this is also termed as Charles' law. You increase the temperature, increase in pressure you will have. Now cooking in pressure cooker. Okay. Because as the pressure inside the pressure cooker increases, the temperature will increase. So the food that we have inside the pressure cooker will cook really fast. So if you draw the PV diagram of it, ideal gas equation is given by PV is equals to nRT. Okay. So if these things are constant, you can say P is 1 by V. Yani there is a hyperbolic curve will be here. Or not following this process, you can say here the volume is constant, only the pressure will change. So this will be a straight line like this. For this process, the volume will be constant. You can see here, this will be a straight line, vertical straight line in PV diagram. V1 is equals to V2. Okay, work done. What will be the value of work done? Because the change in volume is zero, so work done will be zero. There is no work done in this process. Heat transfer is directly given by the change in internal energy, and it is given by, note it down, mcv delta T. Okay. Cv is the specific heat capacity at constant volume. Isothermal process. So isothermal process and isoadiabatic process we will discuss in the next lecture, the remaining part of this thermodynamics. Maybe it will be the last lecture of thermodynamics. Then after we will start KTG. It is the kinetic theory of gases. Okay. So up to this point, if you have any kind of doubt, you can ask. Otherwise, the lecture is been over. Thank you so much for being attentive. Okay. If you have any kind of doubt, you can ask. Otherwise, the lecture is being over. Thank you so much. Bye.